10. And for chapter 10, we are talking about rotational kinematics and energy. And this chapter, again, I don't think so I'm gonna finish it in one sitting, in one recording. I will say I will go into maybe 2 parts or 3 parts. Okay? And just we are going to introduce in this chapter the kinematics, which means we will describe rotational motion the same way that we did describe linear motion. By the end also, we are going to talk about energy and how this is applied when we have objects that they are rolling, or like in general, how to include rotation in our conservation of energy. As we did with linear motion, we are going to start with angular position, velocity, and acceleration. We are going to define the position, velocity, and acceleration. We call it angular from angle or rotational. We will also talk about, in general, rotational kinematics and how we are going to describe a motion with constant rotational acceleration. We will connect between the linear motion and the rotational through the quantities that they are really representing. We are going to talk about rolling motion and what does that mean. And finally, we are going to talk about conservation of energy and including rotational kinetic energy, and we will define a new quantity called moment of inertia. Now, in this chapter, we will cover mostly purely rotational motion, and like by the end we are going to include the combination, but mostly we will talk about an object that is making rotation, and we will only consider here rigid objects. Rigid object means that the shape will not change, so that we will not have any change in the distances between the particles that they form the object. Then it's going to be, we are going to study the rotation motion of a rigid object. Now also, something that we are going to do in this chapter is, since we are having objects going in revolutions or circles or cycles, we will not talk about degrees now. We will use a new unit called radians, and we can of course change the calculator setting now. Now, the things that we are going to talk about here is also, I want you to know that radians, it is not a unit in physics, it is a unit from math. And because of that, sometimes you will find that it's going to disappear. For example, when we're going to talk about next chapter, when we will talk about angular momentum, then we will not have the radians. The reason it is not a physical unit. Okay, here let's talk about an object that is in rotation. That object can be anything from a tire, it can be around merry-go, it can be anything that is rotating. And we are going to define first a reference line, very similar to what we said. This is where we have started. This is here, I'm going to say maybe my theta equals 0. And then I will say, I will measure my theta from the reference line. We will use for measuring theta radians, and which is dimensionless, as I said. Now, also, we need to know here that if we have a circle, a full circle here, like this. Oh, it's not centered. But I will say the arc, if we are going to consider that this is R and this is as a distance is R, this is going to be 1 radian. And of course, if we are going to talk about a full rotation, 1 cycle, it is 360 and it is 2 pi radians. And we will use these in conversions. We need to know that we have signs for angular position and also for, we're going to talk about velocity in a little bit. By convention, when theta is greater than 0, which means this is counterclockwise, this is going to be the positive direction. And when we are going to have the object moving clockwise, is going to be negative. In order for us to convert between, okay, this is something that we need to know. 1 revolution is in degrees 360 and it is 2 pi radians, because these are really very important when we need to convert. Now, this is like from math again. Here, if we have that radius to be R, okay, like I use for it uppercase R, okay, and the arc S, it is the arc length, okay, then here S equals R times theta, where R is the radius of the circle. Then here again we will say we can use this fact or this conversion factor to change units. When a wheel rotates some angle delta theta, we find the angular velocity in radians per second for purposes of dimensional analysis as 1 over s. Because remember, I told you we are not considering gradients as a physical unit, okay? In the same way that we did define the average velocity to be delta x divided by delta t, delta omega average is delta theta over delta t, and it has units of radians per second, or you can say only per second. The instantaneous, of course, is going to be the derivative of theta with respect to the time. One thing that we need to know that since we are considering rigid objects, then omega is the same for all particles, regardless where they are sitting. Also, we can define the angular velocity, the angular acceleration, and the average as delta v over delta t for the linear acceleration. For the angular is going to be delta omega divided by delta t, and also the instantaneous alpha, it is the derivative of omega with respect to t. The units we are using here also radians per second square. Okay, here, I don't know if you still remember when we have the relation between, we said the direction of the velocity, the linear velocity and the linear acceleration. We said when they are in the same direction, the speed is going to increase, and when they are in opposite directions, the speed will decrease. And it's the same here. When you have, let's say in this one here, omega is greater than 0 and alpha is less than 0, which means they are in opposite directions, then the angular speed decreases. And also here, when they are in opposite directions, okay, speed decreases. we can have them increase when they, we can have the angular speed increase when we have the alpha and omega are in the same direction. Let's try solving this one here. A spot of paint on a bicycle tire moves in a circular path of radius 0.33 meters. When the spot has traveled a linear distance of 1.95, through what angle has the tire rotated? Okay. Now R, of course, it is 0.33 meters, and S, it is 1.95, and it is clear that theta is going to be S over R, which is 1.95 divided by 0.33 meters, and that is 5.9 radians. Okay, then this is here showing us the relation between angular displacement and linear displacement. Again, here we have a bird, particular bird's eye can distinguish between objects that subtend an angle no smaller than 3 × 10⁻⁴. Then this is like, this is the bird in here, okay, and looking over, okay, and this is really the angle here that is going to be 3 × 10⁻⁴. How many degrees is this? Okay, of course, if I want to find how many degrees, we can convert from radians to degrees, and then you're going to multiply 3 × 10⁻⁴ radians 2 times 360 divided by 2 pi radians, and this is going to be 0.017, which is 0.02 degrees. How small an object can the bird just distinguish when flying at a height of 100 meters? Then if we're going to assume that that bird is actually at 100 meters height, then what is going to be like I will say the length of the object that is gonna see. R is 100 and theta is 3 × 10⁻⁴, and I'm looking for the arc length, which is S equals theta R, 100 meters times 3 × 10⁻⁴ radians, and this is going to be 3 × 10⁻² meters. In the same in the same way that we dealt with linear motion, we're going to deal here with rotational kinematics, and we are going to introduce the same exact equations that we did use before. And I will say every x will be replaced by theta, every v will be replaced by omega, and every a is replaced by alpha. Then my equations that I'm going to use here, they are listed. Omega equals omega 0 plus alpha t. Theta equals theta 0 plus 1/2 omega 0 plus omega times t. And theta is theta 0 plus omega 0 t plus 1/2 alpha t squared. And omega squared equals omega 0 squared plus 2 alpha theta minus theta 0. These equations are really dealing with situations when we have an object that is rotating with constant angular acceleration. Let's apply these here. I have a wheel that is 33 centimeters in diameter, and I advise you, so that you will not forget right away, find the radius. Accelerates uniformly from 240 RPM to 360 RPM in 6.5 seconds. how far will a point on the edge of the wheel have traveled in this time. As I said, we have calculated R. Now, omega 0, it is in units of revolutions per minute. I will say the people in the outside our physics class, they are not aware of the radians. And this is the reason why we are using that unit, which is more practical. I like here to calculate my omegas in radians per second, and this is the how I will change units. 240 revolutions per minute. 1 minute is 60 seconds and 2 pi is 1 revolution. I was able to calculate omega 0 to be 25.1 radians per second and omega as 37.7 radians per second. By the way, you might find in the problem solving that the solution is different. This is why I intentionally did that, so that you know that for these questions you have more than one solution, and it's going to open your eyes on methods to solve. Usually when I deal with kinematics, I like to have this table, which is the 8 cells here, where I will just summarize my known quantities and my unknown. Omega 0 is radians per second, 25.1. Omega is 37.7. And the time is given and theta is given. And if I look at these equations here, I will find that there is one of them that is gonna match my knowns and unknowns, and I know that my initial position, angular position, is 0, and then theta equals omega plus omega 0 over 2 times t, and I was able to calculate my theta as 204.1 radians, and then I can calculate S as theta R equals the radians times the meters, 33.7, which is 34 meters. Okay, then you're gonna look at the second solution, and you're gonna look at it and see the difference. Here, this is a circular saw, and a carpenter is shutting this off. It has 10 inches diameter, and it slows from 4,440 to 0 RPM in 2.5 seconds. What is the angular acceleration of the blade? What is the distance traveled by a point on the rim of the blade during the deceleration? What is the magnitude of the net displacement of a point on the rim of the blade during the acceleration? Again, the diameter is given. I am more comfortable with working the SI units, and this is the reason I will convert all my units. Okay, maybe I don't need that conversion. Maybe I will not use it, but I like always to have my numbers in centimeters instead of inches. Now, omega 0 here, it is 4,440 RPM, and omega is 0 and t is 2.5. I like first to change units of omega 0 to radians per second, and I did this here, and it is 465 radians per second, and alpha can be calculated as omega minus omega 0. This is the equation that I did use. Like I have derived my equation from this one, and I was able to calculate my alpha to be negative 186 radians per second squared. I want to bring to your attention here that don't do this. Don't say it is 465 divided by 2.5. This solution is completely different because it's talking about something different, that the initial was 0 and the final was 465. Another solution is like I can keep my my omega in revolutions per second. It was given in revolutions per minute. I can change it into revolution per second so that I will not mix units. And then alpha can be calculated as negative 29.6 revolutions per second square. I can confirm that the two answers are really the same by having a conversion, and I did that just to confirm. Now, what is the distance? How many revolutions first? And then I can say it is 74 revolutions per second, the speed. And then it will go to 0 in 2.5 seconds. And how many revolutions theta is going to be? I can use this equation, and it is 92.5 revolutions. I can change my revolutions into radians by multiplying by 2 pi. Okay, these questions are very interesting because they are mixing units so that you will be able to notice the relations between them. And then finally, I will be able to calculate delta theta equals delta S over R, which means I can calculate delta S as R times theta. And I was calculating this as 73.8 meters. Now, if I didn't say which unit I want, you can keep your units in whatever unit you like. Now, the last part is asking about the displacement. And we should calculate like in revolutions. In revolutions, 92.5 revolutions, which means is gonna 92 complete and then 0.5. Now the displacement, then I will say that is gonna go in cycles like 92 of these, and then the last one, it will not complete it. It's gonna do only half of it. Then wherever my object is gonna start is gonna complete half a revolution, then is gonna make that type of displacement, and it's going to be always 10 inches from the beginning because it is the diameter. I'm going to